Okay, so I'm going to talk about category theory parsing command line options. If you have any questions, feel free to paste them into the chat. I will try to monitor to answer them. I also pasted the link to the article itself if you want to read it later at your own pace. Anyway, so if you ever wrote a program bigger than a few lines of code, you probably noticed that the bigger program gets, the harder it is to make sure it does exactly what you want to do because of all the unintended interactions between different parts of the program. There's several ways of managing those interactions. And one of those involved using functional programming and category theory. Category theory is a branch of math which talks a lot about composing different parts. Anyway, so we're going to look at consuming structure arguments from user. Arguments has two fields, binary name and number of jobs. If you are to implement this in imperative way, you would write something like this. So you initialize empty variables, you go over the arguments from the operating system, check each argument if it matches, save it or not save it, then collect the result or panic. This approach doesn't scale very well because it's already looking pretty ugly. This functional approach, by the end of the stack, we will be able to write something like this. So instead of describing how we want to get the argument, we describe what the argument is. So bin, we want argument dash dash bin, parsed as string. With jobs, we want argument dash dash jobs, parsed as u32, and some magical way to collect it and pack it into structure args. In the library itself that's I implemented, you would use macro, so you won't have to write this ugly part. Let's see how we can get to this situation. So for the start, I want to introduce a magical way that for every parameter I pass on a command line, we somehow put it into variable. The struct magic where static string inside is the parameter we pass. So for example, if we pass dash dash bin hello, it gets packed into magic hello and stored as a variable bin. We also will need the way to extract the value out of magic, and for that we use a simple method run. This works and we can consume arbitrary string arguments. Let's remember we've had argument jobs. And for that argument, we need to be able to represent numbers. In Rust, to represent different types inside the same structure, we usually use generics. So we change our magic to be generic type instead of containing static string. And our magical way of creating generates magic with static string, but parser needs to give magic with u32 to user. So for that, category theory contains an abstraction called functor. Functor allows to change a value inside the context to some other value of the same or different type without changing the context itself. This sounds a bit complicated, but if you ever used a method map on option or result, that's more or less what it does. So we extend type magic with method map. It takes the magic value, it takes a function and applies a function on the value inside. With that, we can parse numeric arguments. Okay. So functor needs to follow a few laws, but as long as we only change the value without touching the context, it would work. So this works, but if user passes something that is not a number, for example, a string 42, this from string and unwrap I used here would lead to runtime panics. Panics are bad, and we want to handle it in the application itself. Usually in Rust, you use result data type to contain, to represent failing computations. So we change the magic data type to contain a result instead of the value itself. Function run changes a little bit. So it now returns a result. And we can implement function parse that applies a function that can fail into the value inside the magic. If the value is still there, we try to transform it. This f might or might not fail. If it failed already, we just can retain the error message. So because of the type changed, we have to change map. We can either implement it from scratch, it's simple, but we can also reuse function parse. So with that, I wrote a few examples how this parse can be used. And jobs 42 gets parsed as 42. If you pass string, the computation will give invalid digit found in string from this method. So at this point, we can parse any string, any arguments of any type, and we can also handle the failures. Now that each parser for each individual argument separately can fail, this leads to a different problem. So suppose we are consuming the same bin and jobs arguments. We can start the executing application consuming bin as consuming jobs. But depending on where we start using bin, it might lead to unexpected results. For example, at this point, we don't know if jobs are correct. So to make sure that parser either succeeds when all the arguments are correct or fails when any of those fail, we need a way to compose computations. So in category theory, there is a different interesting abstractions called applicative functor. It allows to run functorial computations in sequence, unlike plain functors. But you cannot use results from previous computations to define subsequent function. That would be a monad. Again, this sounds very complicated, but if you used option zip or result zip, this is very simple to applicative functor. So the idea is we have this method zip. It takes two magic computations with type T and type R. If both of them succeed, we plug them in a tuple. If either fails, we pick error message and retain that. So with that, we can take computation for bin, computation for jobs, and combine them into computation for args. So this way, when we run args, we know for sure that both values we care about are successful. So zip deals only with two computations, but we can chain multiple of them to create monstrosities like that. And later we can flatten it with map. In the library I'm talking about, the macro deals with that stuff, so you get what you want. So next interesting way to compose different computations is, suppose we have two computations. We don't care which one succeeds as long as one of them succeeds. For example, in the application, a user needs to pass either a nickname or full name. And we don't really care which one the user passes as long as one of them is correct. So category theory contains abstraction called alternative function. If the first one succeeds, we use that. If the second one succeeds, we use that. If they both fail, we just retain one of the failures. So in Rust, this can be implemented as this method out. And I wrote an example that user passed no valid nickname, but a valid full name. Computation name composed from nick and full name gives us Bob the Magnificent. Since zip is not constrained by any type, it's not limited to single arguments. It can be arbitrary difficult computations tree. For example, you can compose parsers for subcommons and so on. So next, we can implement two interesting computations. One that always succeeds and one that always fails. In Haskell, those live in applicative and alternative functions, functors, respectively. Here I'm just placing it separately. So pure puts a value into minimal value context. In case of magic, that's okay. And fail just creates custom error message. So with that, we can generate custom error messages. For example, we check if user passed nickname. If not, we check if user passed full name. If not, we fail with the error message that prompting user to specify one of those. And we can fall back to just any value we want. If user didn't pass any of them, we just decide he was anonymous. So far I defined those 7 operations that we need. And those 7 operations are enough to create arbitrary computation tree. So we need a way to run computation, apply pure transformation, apply failing transformation, compose 2 computations either sequentially or in parallel, always succeed or always fail. So with that, you can create a whole bunch of different parsers already. For example, parser that falls back, parser that checks if user passed a value and returns it wrapped into sum, or alternatively returns none if user didn't pass. Looks like this. So we take computation, we wrap it into sum, compose it with computation that returns none. Or you can apply the check. So if your parser expects numeric value in a certain range, you can use a function like guard to generate custom error message. So this works, but at the moment it relies on the magical way to put in arguments inside magic. It's not very efficient. Let's go back to beginning and try to implement some practical implementation. So I start by representing an argument by keeping its name around and by capturing all the arguments into B3 map, going from argument name to argument value. For example, if the application was invoked with -terpin hello -jobs 4, it can generate a map looking like this. Since the argument only contains a name, doesn't have the value until the execution phase, we still need a way to run it. So we change function run to take the argument and list of arguments. And because we'll have to support different types, we will have to introduce different structure. And where you want the same set of operations on different structure in Rust, you would use traits. So one method in the trait is run with this type. So parser for argument would return a plain string. So it takes the argument containing name, it takes the map of arguments, and it removes it and just returns it. So next operation we had was operation map. In case of magic, we could apply it directly. In case of trait and postponing the transformation until the execution phase, we have to stash the computation and the transformation somewhere. So I introduced this structure called parse map, which contains inner parser and contains transformation function. So we extend trait with operation map, which takes any parser and pure transformation and simply packs it into the structure. And the interesting part for parse map is function run, which first runs inner parser and simply applies the transformation to the value the inner parser return and returns result. So next function was parse. Again, it looks very similar to parse map, but this transformation is going to be failing. And the only difference between parse and parse map is that here we don't wrap it into OK because the mapper would do that. So in case of a zip, we also need to stash both computations. And the interesting part about that, you run first left computation, then right computation, and back the results. Pure and fail are simply structure that contains either error message or the value we care about, and returns it inside the run. I'm not showing it here. So parse alt contains parser for left side, parser for right side. And the interesting part about that is parser for left and right, they run out independent copies of arguments. So the only interaction is checking which one succeeds. And we adjust we copy if the right one succeeds, we move the arguments from the right side to the arguments. And with that, the only thing missing is a way to execute whole parser. So it's simply asking a trading system to give us all the arguments and passing them, collecting them into this B3 map and running the result. So with that, I went over how you would implement very simple command line parser, how you can break down different computation into primitive parts. So based on that, there is a library called Baykov, which is command line parser. Its functionality is the same as CLAP, but it takes about 5 times less to compile. It takes 5 times less space in your executable. It supports dynamic shell completion, colorization, human-friendly error messages, and well, let's say it's much more flexible than CLAP is, because all the computations, all the compositions you can imagine, you can implement using how much would it take to support simple flags with no value, like quiet, dry run, and so on? The library Baykov I'm talking about supports them. Let's see. Short. So you would do in combinatoric usage. You describe that you want a short argument, short message, call it switch, and you get a computation that returns bool. And some example how it runs.
But to Andrew's question, is like the for the illustration in the article, in your article.
For the illustration in the article, I would have to go from this B3 map into different structure. It should be something about mix of queue and the map.